Question 2. Now they want physical properties, so we are not looking at chemical. So when they ask for physical, these are not chemical properties. So we're looking at something like boiling point, melting point, conductivity, density, that kind of thing, right? We know that you might have seen the video of sodium plus water. So a few observations you should know is that the sodium floats on water. So why does the sodium float on water? Because the sodium is less dense than water, so that's why it floats on the surface of water, and then it will start to generate hydrogen gas, because now that is chemical reactivity. Although that is not being asked here, you should know that it gives you hydrogen gas, and the release of hydrogen gas and it reacts with O2 in the air, oxygen in the air, it will give you water again, but this is alkaline in solution. But this thing is very exothermic, so that's why and the release of H2, it can be a very exothermic reaction and can catch on fire because of the H2 reacting with oxygen. The other thing obviously is because sodium is a metal. So when you are a metal, you consist of giant metallic structure, and that giant metallic structure means that you have to break strong metallic bond when you melt or when you boil the metal itself. So sodium has high melting and boiling point, but I'm gonna skip the boiling point. You can put it in if you want to, but we're talking about a solid metal, so before it boils, it has to melt first, okay? Anyway, next bit, they want you to complete the electronic configuration of a sodium atom, all electrons. So sometimes question will specify use or show outer shell electrons. Here they want you to draw everything. So you should know that from the periodic table, sodium shows is 2 at 1. So there is 1, 2, 3. First shell, innermost. Second shell, third shell. This is the outermost. This is the innermost. So you have shown 1 shell, second shell, third shell. So pretty straightforward there. And 1 in the outer shell. So that is the atom, not the ion. Next question is about metals. So this was what I mentioned about metallic bonding, where you have this electrostatic force of attraction because you have a positive charge and a negative charge, but it's between the metal ion, the cations, and the sea of delocalized valence electron. Malleable. Malleable is to do with hammer into thin sheet, okay? Be hammer into thin sheets, okay? When you apply force on it, when you keep on hammering, this layer can slide over each other easily, okay? So the layer of cations can slide over each other easily upon application of a force, upon application of an external force. Well, when you apply force and when you hammer it, then you can slide over the so one whole layer can slide over, and you get like a different arrangement of the layers. As for why you conduct electricity, you have these free electrons that allow you they move freely, okay? So the presence of free delocalized is the outermost shell electron. It's not all your electrons, okay? So it's called valence electrons, or you can say outermost electrons, okay? To move freely, okay? That allows you to conduct electricity. How easy it is to reduce the metal oxide. So you got to talk about most reactive and least reactive. So this one is not reduced by carbon at all. Okay, that one is not reduced by carbon at all. So we can think about so carbon can reduce the not so reactive metal. So this is not reduced by carbon at all. So calcium is actually a pretty reactive metal. I hope you know your reactivity series that calcium is actually quite far up compared to silver and iron 3, right? So we can decide calcium oxide as the most reactive, and the least reactive metal would therefore be the one that is easiest to reduce with carbon, and they will have to be silver oxide. Oops, they just want the metal, so I've done a mistake there. Okay. Yeah, because you don't even need carbon to reduce it at all. And then between titanium 4 and iron 3, titanium 4 require high temperature. It wouldn't work at a low temperature, so you need a bit more effort to reduce it. So it's got to be a more reactive metal compared to iron. Okay, so I hope that is quite straightforward there. Question 8, say bismuth is a metallic element, group 5, so 5 outer shell electrons. They want you to show the structure and bonding. Okay, so you need to show structure and bonding in a typical metal. You need to label. Okay, so there's the metal there. You should show the electrons somewhere in between because you know where the electrons come from, right? The electrons come from the valence electrons that get delocalized, right? That's why you get a C of delocalized. So that is the C of delocalized valence electrons. Valence refer to outermost. This is the cations. This is the bismuth cations. After you delocalize the outer shell electrons, that's what you get. Alright, you should have the electrons inserted in between, because if each of these is positively charged, if you don't have electrons in between, then you have a positive and positive, positive and positive. Wouldn't they repel each other? Alright, therefore you have the electrons in between where they were attracted to each other, yeah? Okay, so I labeled it already. So metallic bonding. What is the metallic bonding? It's an attraction between electrostatic force attraction between metal cations. Well, technically metal, I guess. Metal cations. And the C of delocalized valence, or you can say outermost electrons. Alright. 3 physical properties typical of most metals. So we can talk about metals are malleable. Okay, but they want described, so meaning to say they can be hammered. So if you just write one word that is not describing, can be hammered into thin sheets. So that is just like the idea is there. Okay, ductile. So metals are ductile. That means you can be drawn into, or you can be shaped into thin wires. So think about copper wire for the internet. Before fiber optic came along, you have copper wire, right? Copper wire internet, the ADSL thing, yeah. So there was making use of the ductile property of metal. So they make the copper into very fine wire to carry data, yeah, to carry the internet data. But that was a long time ago, before fiber optic, which now is quite fast. All right. The other one will be high melting and boiling point, partly because of the strong metallic bond. Okay, next bit. So bismuth, which is Bi plus chlorine, they want you to form BiCl3. Alright, the most common mistake again is leaving it just like that without balancing equation. So you got to remind yourself, chemistry, balance equation automatically, yeah. One bismuth there. Okay, 3 chlorine, I've got 2 already. 3/2. I think I've shown you again and again that I like my fractions. There's nothing wrong with this. All right. You might be one of those people who either as a teacher or as a student you don't like fractions. I'm fine with that. You can multiply the whole thing by 2 and you can get 2, 3 and 2, and both of which will be accepted equally. So it's just up to you how easy it is for you to see. Most important is you cannot change the number at the bottom because that's part of the formula itself, bismuth 3 chloride. So there's actually bismuth 3 plus and Cl minus. Not necessarily bismuth 3 plus all the time, but it's bismuth plus 3, chlorine minus 1 in terms of oxidation state. Yeah? And this is molecular chlorine, Cl2, so you can't change the number at the bottom. Alright, Next bit, they tell you they want the formula and they want of the ion. So if you forget the charge, then you're not going to get the marks because they specify for you ions. All right. There are 2 bismuth, so Bi2. There are 1, 2, 3, 4, 5, 6, 7, 8. They are 8 chlorine. And if you write like that is wrong because you haven't included the charge yet. You can write in a square bracket like 2 minus. Alright, square bracket because they use square bracket there. If you don't like the circle, the minus, you can just write 2 minus like that. Okay, or you can even just Bi2Cl8 2 minus. That would be correct as well, of course. Yeah. So pretty straightforward there. Okay, to be honest, I don't like magnetic particle theory, but it's one of those things they always like to ask in O-level, and it's becoming popular in A-level question as well. Yeah. Okay, so you gotta know your kinetic particle theory. Next bit, copper. Copper is a metal, right? So it has a giant metallic structure. So melting copper, what are you breaking then? It requires breaking the strong. You gotta specify the bond, which is called metallic bonds. Which one is it between? It's between the cations, the copper cations, and the C of delocalized valence electrons. It's important that you specify all of these, the strong metallic bond, and it's also important that you specify between what and what. It's not between cations and anions because this is metallic bond. So metallic bond is really between the cations and the C of delocalized valence electrons. Getting this explanation correct will also help you when you go on to, let's say, doing A-level chemistry, because it's the same explanation required in A-level chemistry unless you choose to be over-simplistic at O-level. Alright? So therefore, high melting point because of the emphasis on the strong bonds that you need to break between what and what. Okay? Okay, next bit, they want to say molybdenum steel is a hard alloy. So you got to talk about metallic structure, why the molybdenum steel is much harder. Okay, when you think about alloy, okay, alloy is a mixture. All right. So think about iron and molybdenum. So blah blah blah. So after chromium in the same row, there is iron there. Okay, so meaning to say molybdenum has one extra shell than iron. So which one do you think is bigger in size? Molybdenum has one extra shell than iron, which is in the first row of the transition element. Molybdenum is the second row. This has one extra filled electronic shell than iron. This is going to be bigger than this as an atom. Okay, so I can draw big molybdenum, smaller iron, big molybdenum, smaller iron. I'm just drawing randomly, really. I mean, it's a mixture, right? So you could imagine things like this. Okay, I don't know, like this. Big one molybdenum, small one. Maybe I can shade it so that it's clearer. Okay, smaller one iron. Okay, so alloys are mixture. Alloys are mixture of different metallic elements. Because they are still mixture, they still retain the same atom there. Okay, so what happened is these are the cations, but then obviously you have electrons, electron. You could even have electron in between, electrons in between, electrons somewhere. So these are essentially the cations. All right, so they are the cations suspended in the sea of electrons, right? And when you think about it, whether the electrons come from molybdenum or the iron, they are still electron. Does it matter? Electron is electron, so they are just suspended together. So it doesn't matter the electrons come from iron or molybdenum. What is important is the cations will have different sizes. All right. The individual moly and iron cations will have different, I could call it ionic size, but I guess you can just call them different sizes. Okay, prevent from the layers. So we're talking about this kind of thing, layer, right? So if you have normal metallic bond, they are all the same size, so they can slide over each other easily. That's why property of metal is that it's malleable. You can hammer into thin sheets because the layer can slide over each other. All right, prevent the layers from sliding easily, from sliding or moving easily, therefore very hard. If you can slide over each other, that means you can move, right, layer by layer. So that's why metals are malleable. All right, you can hammer into thin sheets, but not alloys such as this, because you have different ions of the different sizes. Yeah.